Welcome to the On-Premise IT Roundtable podcast, the only show that dares to be both on topic and usually on location. Each time we meet, we bring together a group of IT luminaries to discuss a single concept. In this episode, we're discussing the SSD era, or rather, the end of the SSD era. Before we begin, let's quickly meet who's on the panel today.
Hello, my name is Moshe Twito. I'm the CTO and founder of Pliops. Before Pliops, I worked at Samsung for about 8 years. I was the chief scientist there. We developed IPs and technologies for Samsung, a portfolio of named flash-based solutions from SSDs, disk on keys, etc.
I'm Enrico Signoretti. I work for GigaOM as a storage analyst and everything related to cloud and data management.
And I'm Chris Evans. I'm a principal analyst at Architecting IT. I also do a lot of blogging online and just generally write lots of stuff.
And I'm your host, Stephen Foskett, organizer of Tech Field Day and publisher of Gestalt IT. And you can find me at sfoskett on most social media networks. And I've been talking about storage for over 20 years now. And in that time that I've been talking about storage, I've seen changes in the era. We had the storage array era in the 90s. We had the hybrid storage arena once flash came in. There was a little time of DRAM based storage in there too. We had the flash era, the all flash era, with SSDs taking over almost everywhere. And now it seems like we're going somewhere else. Moshe, this is kind of your career trajectory. What do you see as the progression of storage technology over the last few decades?
First, I think for until recently, at least several years ago, the main focus was to increase the bandwidth of the storage itself. So the SSDs RPM was sorry, the HDDs, the RPM was increased. Then the SSDs were introduced as SATA devices. Then they moved closer to the CPU by PCIe-based SSDs. Currently the NVMe standard, but it seems now that there is a gap that starting to create it between the processing power of the CPU system and the sheer bandwidth that the SSDs can provide. So while the SSD, the storage, keep increasing in performance in exponential rate, roughly doubling the rate every 3 years or so. Moore's law seems to not exist anymore, not to the same extent as it was in previously, let's say 10 years ago. So what we have now, we have the case that the CPU just cannot saturate the SSD bandwidth. And so it seems that a new type of technology is required to close this gap. And this is what we try to do at Pliops.
I think that in general, it's a little bit more complicated than that. I mean, all you said is right. I mean, we worked for years, the entire industry, to make, a better storage, to build something that was faster. It was the bottleneck. And we reached the point where now we have a lot of bandwidth, but actually at the same time, we are asking now for capacity. I mean, QLC is the latest example. And QLC is introducing a lot of issues. I mean, all the way down to, durability and, slower writing cycles and everything. And because of the density, of course, there are interaction between the cells that were not supposed to be there a few years back. So it's this thing that is, changing a little bit now, how we deal with storage. I mean, The first SSD was, very durable. I mean, I remember SLC at the beginning was, good enough, and there was this idea of NAND cells versus was it XOR cells? So there was this idea of durability that it was, well, SLC is good enough. We are talking about 1 million writes or whatever it was at the time, and now we are talking about 1,000. And still, yes, we have bandwidth, we have everything, but everything looks much more complicated. Tiers that were not there a few years ago. So we have SLC, MLC, TLC, QLC, and maybe PLC later in the decade. I don't know. So that's something that is complicated things a lot.
I guess I'd like to take a step back and just think about exactly what problem we're trying to solve, because on the one hand, over the years, we've moved through multiple tiers. We've gone through hard drives, we've gone through flash, we put stuff in memory, we've cached. And most of the time, we're talking about trying to deal with what is generally classed as the working set. So with the working set might be in memory, but then there's a slightly larger working set that is the current and the most active data sitting on disk or on SSD, whatever it happens to be. Now, at that point, you want to be able to get that workload in and out, and you really don't want to be sitting tiering between tiers or having to worry about data not being exactly brought in when you need it. And I wonder really whether actually the problem here is not that we should have the end of the SSD, but whether we should have more of a hybrid approach, or we should start looking at all the different types of media within SSDs and start building products that can actually allow us to use that media much more effectively. So Enrico said about capacity. Yes, definitely increase capacity, but does it all have to be QLC? Can some of it be a mixture of different types of media? Do we need to go back to hybrid drives? Are we looking to solve a problem of moving on to a new type of media, or we just be more effective with what we've got?
If I can, add more to this, I mean, do we have the same needs that we had a few years back? I mean, I understand, all the hybrid hard drive thing that we had in the past, but actually there are some workloads that really needs this huge data set. I think about AI, for example, and every time you talk with a client with AI needs, they are talking about petabytes and they want to access it, all of it, immediately, and because they have to feed GPUs and things like that that are really expensive. So we have, it's a little bit more complex than that. There are a lot of workloads that can deal with this idea of performance and capacity. I mean, having a small active data set, but now we also have, applications that really need huge data sets. So we are past the point of tiering for these workloads, I think. But that's something maybe still niche, but growing quickly in all organizations.
I think that one of the things that is let's say unique or different for SSDs than what you used to have with the HDDs is that there is a very high variety of SSD type. You have read optimized, write optimized. You have different endurance numbers, different performance. For HDDs, generally just have one, let's say, almost just one metric, which is the capacity. I'm ignoring now the 50,000 RPM or 10,000 RPM that is dead now. You have just one metric to choose from. This is the capacity. For SSDs, you have a lot of different characteristics, and this actually complicates the process of choosing the correct SSD and on which type of servers you put which type of SSD. And one thing that I think is required now is to be able to, and I think one move in that direction is the ZNS drives that are presented now as in the new standard of the NVMe, to have a single type of SSDs and let other different layer to manage it and customize it according to the requirement of the application. So you don't need to invest because the media itself is the expensive part. The NAND flash itself is the expensive part. And by creating such a high diversity, it complicates the process for a lot of customers. So if we are able to just use one or two types of SSDs and then with a different layer manage it, it may have a lot of value for customers.
I think that it's important too to consider what we mean by an SSD. I mean, it's not just a carrier for flash. I've often said that an SSD is basically just a really small storage array. And I think that that's sort of architecturally what we're looking at here. It's a device that has media, but it also has intelligence, and it manages layout and performance, and it does quite a lot of the things that a storage array might do. But the problem with an SSD, in my opinion, is not, well, certainly the media issues that have been brought up are important, but the biggest problem is, frankly, that SSDs are still pretending to be disk drives. And from an architectural perspective, that's actually not all that useful. You know, it's crazy to me that I go and I buy an NVMe, you know, flash SSD, flash drive. I put it in my you know, modern machine with PCI Express and all this, and it shows up in the operating system as if it was a SCSI drive from 1988. I think that's really, for me, the thing that I'd like to see get rid of. You know, why do we have this anymore even?
That's a really interesting sort of step forward to what I was saying about hybrid, because rather than thinking about hybrid in terms of being a mixture of the different media types and putting it on a single device, what you're saying is really we need to move on from the concept of a package which has been built to suit a need and a requirement, perhaps to fit a generic requirement in the market. So an SSD or a hard drive, pretty much you put it into a device and it works in that device generically. It serves all sorts of workloads. It's very efficient at being very generic and very suitable to most things, but that doesn't mean it's suitable to everything. So by actually separating the controller logic from the medium, you're suggesting that perhaps what we should be doing is taking a lot more control at a higher level. And in that example, Moshe, I think you're sort of implying the flash translation layer should be the bit where you make the decision at a higher level of code with things like ZNS and the various other zone technologies that are coming along. But does that not then suggest that really what all we're looking to do is build solutions which you've just got tiers of different media types that we could choose from? That could be anything. It could be MRAM, it could be Optane, it could be DRAM, it could be anything. But then the techniques to actually achieve anything useful come again back into whatever you might call as a tiering or a placement or a caching algorithm. And how are you going to do that in such a degree that it matches the application?
Yeah, we need a level of storage intelligence and sort of a matching of storage to applications. And the thing is, I think we're going to get that whether we want it or not, because if you look at what's happening with PMEM, for example, and you look at what's happening with modern web applications and object storage and key value stores, we're already moving past the idea that one size fits all storage device.
Yeah, and we saw it happening already. I mean, there are more devices or initiatives to take off from the CPU, you know, some of the computational effort. I mean, it's becoming really hard to deal with these devices. Some of these devices can do millions of IOPS, and doing all of these operations, so decide where to put the data, how to organize it, and things, anything that is about optimizing or even encrypting the data is very challenging now. So this is why there are, you know, solutions now that can offload some of this burden to, you know, to the device itself, or, you know, to something that can deal appropriately with this kind of challenges.
As long as we keep treating the SSDs as a block device, I think it's almost inevitable that we get this high variety of different products, because the interface itself is very simple. It allows you to store fixed size blocks with fixed size keys or LBAs, and dictates certain architecture and behavior. What we noticed is that if you look at a wide variety of applications, starting for databases, either relational or NoSQL databases, going through storage appliances like all-flash arrays, etc. If you look at the lower level, you see that all of those solutions has some sort of key value storage technology. If you look at MySQL, databases have the storage engine part, which is many times can be represented as a key value. If you take a look at White Tiger from MongoDB, or RocksDB for MyRocks, which is a version of MySQL, even InnoDB can be looked at some way as of MySQL can be thought of about some sort of key value. After compression, after you do even if you look at simple block systems, after compression and deduplication, then the media is accessed. The value is variable size because of the compression, and the name of the data is no longer the LBA, but rather a signature of the data itself, like we have in the duplication. So one common thing for all those applications is the key value, and this is the way that the high-level application communicates with the media. And here you have a lot of techniques. You have B tree, you have LSM tree, you have a log-based. You have many types of access in the media, and this is why you want to have different placement algorithms and different things to do with for different applications. But if you go up in the hierarchy and instead providing the block API, we provide a functional rich key value API, then we can provide one unified interface with high performance and high efficiency to all of those solutions. And then the question of different types of SSDs no longer exists, because in that case, we just want the simplest SSD that we have, like the ZNS that was mentioned before, the zone namespace, and the placement is already tailored to the specific type of storage engine that we implement. And the application just uses this key value API instead of going through the software base or the, I don't want even to go to how to implement it, to go through this storage engine as part of the application.
So is there not a risk there then, Moshe, that, you know, by using that sort of concept, all you've done is just put another shell around the outside of what is an SSD, and instead of it being called a solid state disk, it's now a solid state key value store. So you've solved one problem by taking it and pushing it down to another level. And that's great, because you've taken away some of the complications. You might be able to optimize by doing that. But ultimately, all you've done is just put another shell around it, and away we go again. Is there not a need to be more generic than just key value, and to have a degree of functionality you can program into this that says any type of interface I want to do, I need somehow to have the device to be capable of being dynamically modified to take whatever protocol I want to do. And it could be a key value store, it could be a block device, it could be anything. So really, should we be moving to solid state? I can't even think of a name, but solid state storage, you know, or solid state data instead of solid state disk and solid state key value store.
Absolutely, but if you think key value is such a powerful abstraction that you can manifest many different, virtually every storage requirement you can express as in a key value language, including block. Of course, block is just a special case of key value. So if you have a tunable and flexible enough interface, you can, as you said, you can program the behavior of this layer as you wish. You can optimize it to writes, to reads, to space, whatever you like, and then use it just as the application requires. Because block is very far from the abstraction of block is very far from the origin of data, and all of the translation layers that are currently fixed, and as I said before, have different characteristics for different applications. Now, once you have this key value, you can program it exactly as you said. You can program it to whatever you like. You have this simple media, which is very simple, very close to the original. No FTL inside. Everything is block based, etc. And all the programmability is in this intermediate layer that I'm talking about.
Yeah, I think that one of the points that you're making here that is really interesting. Well, for one thing, it is interesting to consider that block really is just a key value store, and it has been for about 30 years since we moved away from physical addressing of media to logical addressing of media. It's essentially been a key value store this whole time, but that's not how we use it. How we use it is as the world's stupidest storage layer. I mean, we basically just throw things at it and hope that it can do something appropriate with the data that we put on it. And then we put more value added intelligence on top of that. To me, this sounds a little bit like what we're talking about with computational storage and with some of these disaggregated system architecture concepts, in that we are moving not just intelligence, but sort of purpose fit down into the media instead of having it be such a generic store of data.
Well, at the moment, I think that all these initiatives, I mean, new protocols, new approaches are, meant to simplify the stack. I mean, as you said, we are accessing data still in a very, very archaic way. I mean, the idea of having an hard drive, even if we have memory behind the scene, doesn't make any sense. So having new system that can, at the same time, act as a legacy component, but provide new APIs, new access methods that can take real full advantage of the media in the package. That's great. And also, I think that more we will enter in this era, if we can enter a new era, more the application will be optimized for it, because developers are not used to have, maybe let's call it a specific drive or a specific optimization for an hard drive. Now we can say, okay, we have additional tools, and if we had this, 2 lines of code or whatever it's needed, we can have 10 times the performance. That's can really change the economics of current server models, and you can again access more data more quickly and more efficiently, because there is also this problem of efficiency in most data centers now. So it's not about capacity, it's not about performance, but it's also how can you fit enough resources in a server to make it more dense, or more power efficient from the all types of efficiency.
Yes, I totally agree with that. And indeed, once you use the key value API, most of the operations that you want to do from high level are much simpler. Think about implementing a file system instead of over block, over key value. It is order of magnitude simpler. You don't need to deal with all the block allocations. You don't need to deal with many things that currently take a lot of effort and congestion and locking and things like that. Block is a special case. Storage engines, of course. And now you don't need to go through this layer and develop it, because currently every type of database develops its own storage engine. Cassandra has its own, MySQL, MongoDB, and all those applications requires key value in some way or other. So by having that, you just simplify the life of all the developers of all storage-related applications.
I'm interested to see how we might think it might simplify some things, and without a doubt it does. Some of the things you just said there, Musha, around the idea of implementing, for example, a file system where you can write the file system much more simply because you're writing key value entries rather than having to deal with blocks. But what does it do for certain areas where it might make things more complicated? So for example, data protection. Today, we might be used to the idea of putting in a dedicated RAID device that would do that protection for us. If we're putting in physical disks, sorry, we shouldn't call them disks. We need a name for them, don't we? We need to call them solid state media, SSMs then. If we put in solid state media, what do we do about things like data protection? So who does that task now? Are we going to now require that the application does more of that, and that becomes a higher level function? Or are we going to put another abstraction layer between our solid state media and the application that offloads some of that functionality too? How far do we go in pushing bits and pieces up and down that stack?
I think it's a great question. And what the direction that we took in Pliops is not that of key value SSD, let's say like Samsung initiative, but we have a storage processor that manages several SSDs. So, and actually, one of our offering now currently is disk fail protection, because once you manage 8 SSDs, let's say 4, 8, 12 SSDs, you can do all the protection that is required from that intermediate layer. And you can control the striping of the data, the placement, the balancing between this protection and more by having this. This is why I said it's an intermediate layer that we implement in hardware and accelerated by hardware. But I don't want. It has a lot of benefits from a CPU perspective, but the essence is to have this layer because we manage multiple disks. We can also provide data protection, and this is one of and we provide data protection also end-to-end protection and protection RAID-like features, protection against disk fails.
I don't want to be controversial, but isn't that just creating a better RAID controller? At this point, is there something that at essence we need to be doing more than just creating another RAID controller that's managing less intelligent disks? Because isn't that what RAID did originally? It gave us a redundant array of effectively inexpensive or dumb disks that we moved the brains out of. So what's the difference here between what we did before and what you think you're doing, for example?
So RAID is just one aspect. You asked about the ability to provide data protection, and I answered that we provide data protection similar to RAID cards, but this is just one aspect. We also have, and if you just look at block interface again, so if you look at block, and we provide also block, we expose, beside the key value API, we also provide the block API just for backward compatibility and ease of integration and ease of integration. So if you look at the block API, and then you can look at that as just another type of RAID, much higher performance, a very low performance degradation during rebuild and stuff. Very good RAID, but it's basically, you can look at it as a RAID card. But we also have the encryption, we have the compression, which is seamless. You don't need to manage the compression. It's not just the compression acceleration, is the handling of the compressed data. And this is just for the block API. On top of that, we can also have more functionality in the key value API. And then you have key value interface, high performance, and we also protected against disk failures. So RAID is just part of the value that we provide.
So are we talking here more as storage accelerator? We are seeing graphic accelerators, we are seeing network accelerators now, and this is a storage accelerator. So we are accelerating everything that is close to the CPU to offload some task from the CPU itself, so that it's free to do what it's meant to do. I mean, doing some compute jobs instead of doing storage, networking, or whatever else jobs. So is this the goal of this new architecture approach? I mean, or there is something that I'm missing here?
No, I don't think you missed anything. The crux here is indeed storage accelerator, and you accelerate, but you accelerate both traditional block-related um, operations or functions like compression, encryption, erasure coding, thin provisioning, things like that we provide in our block API. But also, again, the much stronger API and much more flexible of key value. But everything eventually is related to storage, and we and I think other solutions that will come in this area accelerate storage related operation. And I treat key value as a storage related because it's so ubiquitous in many applications and it's very tied to the storage. Currently, it works over a file system, over block, but it is there already. It's not something that we invent. There is key value is already very popular, and just by offload it and make it much more efficient, you can provide higher value.
I'm going to ask you a question, Moshe, because I'm interested, as we've gone through that discussion, to think where this might lead, because currently we think of everything as a peripheral that sits at the outside of the central compute. And, you know, Enrico was just talking about that in that scenario. And I'm wondering whether, if we're saying that we don't need solid state disk and everything's going to turn into, say, key value or something much more abstract, that architectures that connect devices to the memory bus and give us more connectivity directly into the CPU or even into a GPU complex could be part of this discussion. You know, we have to maybe step away from the concept of a peripheral, a separate device that we do block IO to that's on a completely separate bus. And now what we think is we're pushing a lot of this technology closer to the CPU, closer to GPUs, and using more generic functional APIs to talk to them. And that's completely changing the architecture of the way we build infrastructure in general.
Yes, I think it's a very interesting direction, and quite radical change. And in reality, I think it's best to advance, you know, in small steps, because this industry is very traditional. As you all said, we have architecture of decades ago still prevalent in the storage. So this is by the way why we also have the block API, which is simpler and beside the key value. And actually, for our next generation product, we are talking about adding CXL exactly for the purposes that you mentioned, to be able to be part of the memory hierarchy, memory mapping, memory space, and be able to fuse our solution into the memory memory space.
So to sum up then, let me just ask my guests, and we'll end with Moshe. Enrico, are you convinced? Have we reached the end of the SSD era?
Well, actually not, but I'm sure that we are reaching the maturity of SSD era. I mean, now that we understand better what we can do and the needs of, you know, all the organization that use this kind of media, now we can design solutions that are more aligned with this new type of storage. So, and this is why we are seeing, you know, many of these, you know, new approaches surfacing. So that's my opinion.
Yeah, I think I agree with Enrico. I don't think we're necessarily going to see the end of SSDs, just like we never saw the end of tape and we didn't see the end of disk. But what we did see with those technologies is that something came along that could do something better to fit the current requirements, and those other mediums sat in the background and served a purpose, you know, in their own right still. So I do think that we are ready for a change. We need a change. We've got new data types. We've got new architectures internally to make this work. We've got GPUs coming in that are very different to what we would have seen 20 years ago. So there's lots of other technologies coming in that are driving us to need to change. So I think we're definitely on the cusp of change. And I would imagine that SSMs, or whatever we choose to call them, will be something that will definitely fit that market, whilst everything else will sort of still be there anyway, just like it's always been.
Yes, exactly as GPU didn't eliminate CPUs, and same for TPUs for AI or any other FPGA or any other technology. As Chris Enrico said, there is space for everything, but currently there is a strong requirement for some sort of storage acceleration to be able to extract more from the media, from the media itself, that can provide very high performance. But currently, a lot of this performance is eaten up by inefficiencies in the stack, and this part call for new type of devices, for architecture with storage accelerators. But conventional SSDs are here to stay, I think, for quite a time.
Yeah, as for me, I would love to see the end of block storage, but it hasn't happened yet, and I'm not sure it's going to happen this time either. I mean, as you say, Chris, it's not like we're going to lose it forever completely overnight, but at the same time, I'd love to see less emphasis on it, which is what we've been seeing over the years with file-based storage and object-based storage and cloud storage. So I think that we are actually reaching the end of the era in which SSD is considered an essential compute element or an element of the stack and is instead just another bit of infrastructure. So to leave it there, thank you very much, everyone, for joining us here for the On-Premise IT Roundtable podcast. I'd like to quickly go around and ask, where can people connect with you and learn more and continue this discussion? Moshe?
So we have our website, pliops.com. And my email is moshet at pliops.com. So every question, or you can put them.
Thanks. Chris?
Yeah, you can find me at architecting.it, where I write blogs, I write papers, I write all sorts of content, really. But you can find lots of stuff there. You can also find me at Storage Unpacked, where we podcast. And this is the sort of thing we've been talking about recently on some of our recent editions, so well worth having a look there. And if you just want to follow me in general, you can find me at Chris M. Evans on Twitter.
Yeah, for me is even easier because I'm not synonym with an actor, so you can just Google my name and you will find me easily. Or if you're lazy, you can just go to gigaon.com and you will find my profile as an analyst, all my write-ups and the stuff that I do around.
And as for me, you can find me at sfoskett on most social media networks. You can find my writing at gestaltit.com. You can also listen to me on these podcasts every week. Every Tuesday, we do a Utilizing AI podcast. And every other Tuesday, we release another episode of the On-Premise IT Roundtable podcast. Also, you can find a weekly analysis of the news. Just go to gestaltit.com on Wednesdays for the Gestalt IT Rundown. So thank you very much for listening. If you enjoyed this discussion, I know everybody says this, but it really does help if you subscribe, rate, and review us in iTunes. And please do share this episode with your friends, share it on social media, that sort of thing. This episode was sponsored by Pliops. This podcast is brought to you by gestaltit.com, your home for IT coverage from across the enterprise. For show notes and more episodes, go to gestaltit.com/podcast. Thanks, and we'll see you next time.